the radar images at the bottom left and bottom right, two different images from different times, literally showing on radar that sea breeze front as it develops and moves inland. And of course, the picture in the middle, a good example of a late afternoon thunderstorm developing along a sea breeze. So the sea breeze and the land breeze circulations represent daily reversal of winds, a diurnal reversal of wind. It's a daily occurrence where the winds reverse. Also at the mesoscale are mountain and valley breezes. In the valley breeze, the daily heating causes the expansion and upward vertical motion over the side of the mountain, and clouds and sometimes rain. So remember, we talked about the atmosphere, we talked about controls of temperature. That thinner air at higher elevations allows the land to heat up and cool off more quickly because there's less air molecules to scatter or disrupt the incoming solar radiation. So during the afternoon, the side of the mountain will likely warm up more quickly, creating a thermal low, drawing that air up. Whereas the mountain breeze at night, that mountain slope will cool off more quickly at higher elevations. Again, the same reason, the air is thinner up there, and that cool air will then flow downhill under the force of gravity. So a valley breeze happens during the day with wind blowing uphill, and then the mountain breeze occurs at night with those mountain slopes cooling off quickly and that cold air moving downhill at the force of gravity. Those nighttime mountain breezes are sometimes called gravity winds or drainage winds because gravity causes that cold air to drain downhill. A different type of gravity wind, but also happening for the same reason, gravity pulling colder air downhill, and also at the mesoscale, is what's known as a katabatic wind. Katabatic, not too different from the word adiabatic. So a katabatic wind is a downslope wind, but it's going to be typically stronger than those mountain breezes. Those mountain breezes at night are fairly gentle, but the katabatic wind is quite a bit stronger. You have to have a high plateau or an area at high elevation where cold air can sit for a very long time and become colder and colder. And then once that colder air begins to build up and thicken, it will literally flow over the peaks at the top of the mountain and flow downhill, and the force of compression will warm it very quickly. So a katabatic wind is the technical name for a drainage wind, or also a gravity wind. That is a wind that carries cold, high-density, colder air is denser, cold, high-density air from higher elevations down the slope under the force of gravity. Sometimes these winds are also called fall winds or Föhn winds, which is Föhn is a German word for referring to gravity again. So the ideal setting, as you can see in the illustration, is an elevated plateau that's snow-covered and therefore cools the air at high elevation. As the air begins to descend through the gaps and the valleys at the top of the plateau, it can be channeled and can actually accelerate under the force of gravity. And these katabatic winds can be quite strong. As a matter of fact, in Antarctica, they can take up to a hurricane force wind speeds. Another interesting name of a wind, which is also a mesoscale wind, but it's also a gravity or a fall or a drainage wind or a Föhn wind, is called a Chinook wind. Now, Chinook is a Native American name, and it was given to these very dry, warm winds that come down the leeward side of mountains, and Chinook is the Native American term for snow eater, and it's because we could have snow on the leeward side of the mountain, and this warm, dry wind comes down, and literally the snow doesn't melt, it evaporates because how warm and dry the air is. So Chinook winds occur due to orographic lift. And we've had this illustration of the wind, the rain shadow, as winds are lifted orographically. So orographic lift cools air on the windward side of the mountain until it reaches 100% humidity. That's where our cloud forms. Of course, that's saturation, condensation. Condensation, the formation of clouds, possibly even rain or snow, robs the air of moisture while it adds heat. Remember, condensation is a warming process. The air is then forced down the mountain on the leeward side, and it warms at the dry adiabatic lapse rate, and that heats it up and drops its relative humidity. So those Chinook winds are very warm and dry and are able to eat the snow if it exists on that leeward side of the mountain. Now, in Boulder, Colorado, we have winds that are so strong that those Chinook winds oftentimes bring blowing debris with them, and homes on that side of the mountain will have shutters to protect their windows. And here's another example, another illustration of that Chinook wind where the wind is forced up the windward side. The moist air is robbed of its humidity with cloud formation. Condensation warms the air as it's forced back down the leeward side of the mountain. You get a warm, dry air, and you can have a significant difference in temperature between that warm and dry air on what's actually happening at the surface, and those Chinook winds can be quite strong. The next wind is a Santa Ana wind, and the Santa Ana is really somewhere between your mesoscale and your synoptic scale. Not quite weather map size, but beginning to get there. A warm, dry wind that east or northeast, that blows from the east or northeast into Southern California. So high pressure over the high desert of the Four Corners and Nevada creates a downslope wind that's literally forced through the mountain canyons in eastern parts of California, southeastern parts of California, the Santa Ana Canyon, and compressional heating as that wind is forced downhill heats that air and dries it out. As it's funneled through the canyons, it picks up speed and actually becomes a major wildfire threat to that region. So again, the Santa Ana wind only happens here in the southwest corner of the United States, but it's that big dome of cold high pressure over the high plateau, the high desert plateau. That high pressure and the clockwise flow around it forces winds to the Santa Ana passes. They compress, heat, and dry. We get some very fast offshore moving winds that the surfers in Southern California love because it's a warm wind and it blows offshore and cleans up the surf, but it's also a major wildfire threat in the area. Here's a slightly different view of that Santa Ana wind. Again, you get out of Los Angeles and Southern California, you get to the coastal ranges, and then you get to the High Sierra, and back behind the High Sierra, the land mass is really, well, the elevation's quite high, and it's a cold area, big dome of high pressure. High pressure, the air sinks and moves outward, so as it moves outward, it has to funnel its way through these gaps in the mountains, and as it comes downhill from those higher elevations, it warms and dries and creates those strong Santa Ana winds and a big-time fire threat in Southern California. We see that every year when the Santa Anas kick up. Another wind that's transitional from mesoscale to synoptic, but really when you start looking at the region here, it's going to fall into the synoptic scale, is the monsoon wind system. Now, monsoon, when you hear that term, most people just think rain or lots of rain. It's a monsoon out there. Well, monsoon actually doesn't refer to rain at all. It refers to a seasonal reversal of winds. Monsoon means seasonal reversal of winds. Now, in Florida, we have a daily monsoon, meaning during the day we have an onshore flow of showers and thunderstorms, and then at night we have an offshore flow with the land breeze. In the Asian monsoon, the most famous monsoon, it's really seasonal, where in the summertime, we have an onshore flow coming off the Indian Ocean, bringing lots and lots of warm, humid air and lots of rain. And then in the wintertime, the high pressure, the cold high pressure from the Tibetan Plateau, again, another very high plateau, forces air down the mountains, the Himalayas, literally into India and South Asia, and that air is heated and dried and creates a season of very, very dry air. So monsoon wind system is a seasonal reversal of winds, a wind system that changes direction seasonally, blowing from one direction in the summer and the opposite in the winter. In the Asian monsoon, again, the winter months bring high pressure and an offshore flow, while the summer months bring low pressure and an onshore flow. And here is how all that rain plays out. So June, July, we're talking about 120 to 140 inches of rain in India and South Asia. That is when there is low pressure over the Himalayas. Again, the Himalayas represent a high elevation heat source. It's very high up. It heats up very quickly. We get this seasonal low that forms there, and it continues to suck the wind off the Indian Ocean. That warm, moist flow drops all that rain. And you get into October, November, the rain almost cuts off. And in January, there's virtually none, because at that point, we're talking about high pressure that sets up over the Tibetan Plateau. And then you get this tremendous offshore flow. As it comes down the Himalayas, it heats up, it dries out, and you have very, very little rain in the wintertime. When winds throughout the world are averaged over time, the local patterns tend to vanish, and what you're left with is a global scale pattern known as the general circulation of the atmosphere. Now, the cause of the general circulation of the atmosphere, all that wind swirling over the globe, is the same cause as many things in meteorology.
unequal heating of the Earth's surface. The direct rays, insolation, incoming solar radiation, the direct rays of the sun strike the equator at a very high angle and warm it up, and the direct rays of the sun strike the poles at a very low angle, and the poles remain cold. So unequal heating of the Earth's surface has the effect of atmospheric heat transport, where the very warm air at the equator, where there is a heat surplus, moves northward, and the very cold air at the poles, where there is a heat deficit, moves southward toward the equator. So warm air moves toward the poles, cold air moves toward the equators. And oceans also help to transport heat from the equator to the poles and back again. As often is the case in the study of atmospheric sciences, we have to work with a conceptual model, not quite what actually happens in the atmosphere, but a human construct that we can create that closely resembles the atmosphere. We're going to talk about the single cell model and the 3-cell model. And the single cell model is not a good representation of the atmosphere. This is as simple as it gets. Imagine an Earth that is straight up and down, no tilt in the axis, no angle of inclination, an Earth that is completely featureless, so covered with a flat sea, no waves, and an Earth that is not spinning. There's no Coriolis because the Earth is not spinning. So uniformly covered with water, sun always directly over the equator, no seasons, and it does not rotate, the Earth, so no Coriolis. In this situation, we'd have one thermally driven convection cell in each hemisphere, where the hot tropics would produce a belt of low pressure or upward motion, and the cold poles would produce an area of high pressure or downward motion, and at the surface, wind would blow from the high pressure at the surface to the low pressure at the equator from north to south, bringing cold air back south, and in the upper levels of the atmosphere, the warmer air would blow north. And that one circulation cell in each hemisphere would be known as a Hadley cell. And again, those assumptions don't work, so we'll look at a different model of the global circulation of the atmosphere. There is a lot going on in this 3-cell model of the atmosphere, and this is one of those basic concepts in meteorology that then lends itself to climatology that you'll simply have to get a handle on and a grasp on what's happening. And so we have 3 different cells, and if you can see on the left side of the illustration, the Hadley cell, a Ferrel cell, and a polar cell. Now we're going to go through these one at a time, starting with the Hadley, then polar, then Ferrel cell. Then at the surface, those cells, those convection cells, create winds. The trade winds, which is one of the greatest prevailing winds in the atmosphere. The westerlies, also one of the greatest prevailing winds in the atmosphere. Then the polar easterlies, which aren't nearly as significant. So if we allow for a uniform Earth, you can see this Earth doesn't have any land over it, no continents, no mountains, and it's covered with water. But we do allow the Earth to spin. So it's straight up and down, no angle of inclination, but we do allow for the rotation of the Earth and therefore Coriolis. We get a closer approximation of the real atmosphere. So let's start at the equator. We know the equator is hot. We know that hot air rises, and so as hot air rises, it gives up its humidity in the form of condensation, cloud formation, and precipitation. So at the equator, we have a belt. All around the equator, we have a belt of low pressure where air is rising and you get cloudy, wet weather. That's why we have the Amazon. That's why we have the Congo. All right? That belt, if you look on the right side of our planet, is called the Intertropical Convergence Zone, or the ITCZ. That is our area of low pressure. Now, in the atmosphere, that warm, moist air rises. As it gets up in the atmosphere, it is robbed of its humidity. It moves north, as you can see, and then begins to cool as it moves north, and it sinks. So the Hadley cell